Hi there, I'll be talking about the rules for balancing redox reactions for so what are redox reactions? They are reactions that primarily involve the transfer of electrons between two chemical species. And we know that the compound that loses an electron is said to be oxidized, and the one that gains an electron is said to be reduced. But how do we determine which species loses electrons and which species gains electrons? Because it's not very readily apparent when we look at a reaction which species is gaining electrons and which is getting reduced. So we'll first look at some rules how to determine the oxidation number, because the oxidation number tells us whether a species is getting reduced or oxidized. And then once we have seen the rules, we'll take a look at how to balance these reactions. So why we need the rules is because, let's say if we are giving this reaction, lead plus zinc gives lead solid plus zinc ions. So we can see that lead is in an aqueous form, zinc is solid, and then we can see that lead has a charge of 2 positive, and over here it doesn't have a charge, so we'll assume here, we'll go over the rules, but it has a charge of 0. So we can see that this is reduced, so the oxidation number has reduced, so we can tell that lead is reduced. And we can see the zinc has a charge here of 0, and over here it has a charge of 2 positive. So we can tell that the charge has increased. So we can say that it's been oxidized. In other words, it lost electrons. So it is pretty easy to figure out, when it's an easy reaction like this, which species might be getting oxidized and which species is getting reduced. But it's more involved when we're given a reaction like this. We can't really readily see which species here is getting oxidized and which species is getting reduced. All we have here is a negative charge on H2ASO4. This question was in a final in April 2000. So we'll look at the rules, and then we'll see how to work a problem like that. So this is our rule number 1. So rule number 1, when a species is in its elemental form, the oxidation number is always 0. So, for instance, oxygen here, which is very important in redox reactions, we can see that when it's in its elemental form, the charge is 0. Similarly, manganese, when it's in its elemental form, 0. So any species which is in its elemental form has a charge of 0. Okay, so rule number 2. If in monoatomic ions, sorry, the oxidation number is the charge. So this is rule number 2. So rule number 2 is whenever there's a monoatomic ion, the charge is whatever the oxidation number is on that ion. So sulfur 2 minus, we can see right here. Next is rule number 3. Rule number 3 is pretty simple. All the alkali metals always have a charge of +1. That's sodium, potassium, and the halogens, whenever they are at the end of the formula, they have a charge of -1. And then we have rule number 4. Whenever there's a polyatomic ion, oxygen always has a charge of -2. This is very important, and this is the most common rule that we'll be utilizing while balancing redox reaction and while determining the oxidation number of the unknown. So for instance, in all these polyatomic ions, we can see the oxygen when it's part of a compound, the oxidation number of oxygen is always -2. But there's an exception, and that's the peroxides, H2O2, and alkali peroxides. The oxidation number is -1. So this is what these are the exceptions that we have to look at. But 90% of the time in the problems that we'll be encountering, oxygen has a oxidation number, a charge of -2, and the only exceptions we'll be looking out for is peroxides. And rule number 5 is hydrogen. So those are our rules. Hydrogen is almost similar, like oxygen is -2. Hydrogen, again, very common. We'll be using this a lot. So whenever we start balancing a redox reaction, oxygen and hydrogen is what will be our friends. So hydrogen always has a charge of +1, and so whenever it's part of a compound, we can assume that it has a charge of +1. And again, the only exception is when in metallic hydrides, it has a charge of -1. So we'll be looking out for these exceptions, but in most of the problems that we encounter, hydrogen has a charge of +1. And so this is our rule number 6. So that's our final rule. And the final rule is whenever there's a neutral molecule, it has no charge. We can see here it's neutral, it has no charge, the charge is 0. So that's like NH3 and in a polyatomic ion, the charge is whatever the charge is on the top right hand corner. So in the next slide I'll show you how we when we're to balance for instance over here in the next slide I'll be showing you if we want to determine the charge on chromium, we can determine that because we know the oxygen is -2, so how to use the total ionic charge to determine the charge on chromium. So that's what I was talking about, that the oxidation number of all atoms add up to the total ionic charge, which is in this case is -2. So that's what how we determine the oxidation number is when we keep this in mind, that the oxidation number of all atoms it equals the total ionic charge. So now let's look at how to figure that out. So we're given CrO4 and it's got a charge of -2, and we have to determine the charge on Cr here. How we do that is we first write down the -2 charge on the right hand side, and that has to equal the charge of all the atoms here. So we start by writing -2 on the right hand side, then write our equal to sign, and then we know that oxygen has a charge of -2, so we write that in parentheses, and then we know that there's 4 of those, so we write down 4 times -2, and then that's we have to determine the charge of chromium, so we write down an x. So x, 4 times -2 is -8, equals -2, and x equals 8 plus. So we we see that Cr here has a charge of positive 6. So let's say if we want to determine the oxidation number of Cr in Cr2O7, and then the charge on this total compound is -2. So same thing, we write down -2 on the right hand side, and then oxygen always has a charge of -2. We write that in parentheses, and there's 7 of those, and then there's 2 atoms of Cr, so 2x minus 14 equals -2, and add 14 to both sides, 2x equals plus 12, and we find out that chromium here has a charge of positive 6. So once again, we'll reinforce that when the oxidation number is increased, it is oxidized, and the reason is it's losing electrons. So right over here we can see that Fe2 plus is Fe3 plus electrons, so it's losing this electron, so the oxidation number is increased, so it is getting oxidized. And when an atom's oxidation number is decreased, it is reduced, and the reason is it's gaining electrons. So right over here we can figure out that copper has a charge of positive 2, and then over here it's in its elemental form, so the charge is 0, so we can see that it's getting reduced. So the only way it'll get reduced is if it gained electrons. Now that we've seen all the rules on how to determine the oxidation number of species that are losing or gaining electrons, we can use that to balance redox reactions. So suppose we're given a reaction like this, a redox reaction like this, and we have to determine which are the species that are oxidized and which species get reduced. So whenever we are given a reaction like this, we just learned that oxygen and hydrogen are our friends. So we see that there are no peroxides here, and whenever oxygen is part of a compound, we can assume that the charge is always -2. And that's the first thing that we'll be looking at when we're given a reaction is oxygen, and next we'll be looking at hydrogen, and again we see that the charge is positive 1 in both these cases. So now that oxygen and hydrogen, we know that they have the oxidation number that we are aware of, oxygen -2 and hydrogen positive 1. We can look at other measures. So we see that oxygen and hydrogen, they're both part of compounds. So the only ones left are sulfur here and chlorine. So those are the two suspects that we'll be investigating. And sulfur and chlorine. So we find the oxidation number of sulfur, and we see that it's part of a compound with oxygen. So oxygen is -2, so we'll easily be able to find the oxidation number of sulfur here, and we'll be able to find the oxidation of sulfur here, and chlorine and chlorine. So we write down these separately. So we know that SO2 here is getting changed to SO4 -2 here. So we write it down, and we don't worry about the coefficients because those are just for balancing. And similarly, we'll be writing ClO3 and Cl separately, and then figuring out the oxidation numbers. So right here we find out that SO2 is changing to SO4 and ClO3 is getting changed to Cl minus. So we write down SO2, SO4, and then we have to figure out the oxidation number of sulfur in this compound. So how we do that is by the rules that we just learned. SO2, we write down X for sulfur. We start from the right hand side. We know that the charge is 0 on this compound. So we write down 0 on the right hand side equals negative 2 for oxygen, and then there's 2 of them. We write down 2, and then plus there's 1 sulfur plus X. And then we solve it. We find out that X is 4, so the oxidation number of sulfur in this compound is 4. Similarly, on the right hand side, SO4, we write down SO4 and it's got a charge of negative 2. So right below it, we write down on the right hand side that the total ionic charge is negative 2, and the charges on the rest of the atoms must equal minus 2. So similarly, oxygen, the charge is negative 2, and there's 4 of them, and then plus X. And once we solve this, we see that the charge on sulfur here is plus 6. So it's changed from positive 4 to positive 6. So the charge is getting increased. So we can see that it's oxidized because it's losing electrons. So when something loses electrons, the negative charges are gone. So it's more positive. Now if we look at ClO3 and it goes to Cl minus, we write it down here, and ClO3 and the total ionic charge is negative 1. So we write down negative 1 on the right hand side equals oxygen is always negative 2, and there's 3 of them, 3 times negative 2. And then there's 1 atom of chlorine, so 1X. And once we solve this, we see that chlorine has a charge of positive 5. And Cl right here, Cl minus, there's nothing else involved. It's just an ion, so it has a charge of negative 1. So positive 5 to negative 1, we see that it's reduced, the charge is reduced, so the only way it can be reduced is if it gained electrons which are negatively charged. So we see that it gained electrons, so decrease in oxidation number means that it's reduced. So now that we've seen all the rules and saw how to determine the oxidation number, now let's look at how to balance a redox reaction. We looked at this problem in the beginning of this video, and it was in an exam. So let's see how to balance it. The problem asks us to balance this redox reaction in a basic solution. So as I'll be mentioning later on, we have to be careful about these problems, whether they want us to solve it in a acid solution or a basic solution. So this one asks for a basic solution. So there's a few steps on how to balance this. So the first is apply the rules that we just learned on how to find the oxidation number. So what we'll be doing here is we can see that here arsenic is in its elemental form, so it's got a charge of 0, and by the rules that we just learned, we'll be finding out what the oxidation number of As is in this compound and what the oxidation number for As is in this compound. So similarly, what we just learned, because the total ionic charge on this compound is 0, so we write down 0 on the right hand side, equals, now hydrogen is positive 1 like we learned, so we write down positive 1 in parentheses, and there's 3 hydrogen, so we write down 3 here. So 3 times positive 1 and then an x for here. So because we want to find out the charge on AS, so that's x. So x plus 3 equals 0, and so that it means that x is negative 3. So the charge on AS in this compound is negative 3. So similarly, we'll find out what the charge on AS is in this compound. The total ionic charge is negative 1, so we write it on the right hand side, equals, now oxygen is negative 2, so we write down negative 2 here. There's 4 of them here. 4 times negative 2 plus x, that's what we want to find out, plus hydrogen is always positive 1, and there's 2 of them, so 2 times 1. So 2 plus x minus 8 equals 1, negative 1. And once we solve that, we find out x is positive 5. So we can see that in this compound here, arsenic has gone from a charge of 0 to negative 3. So it's reduced. The charge has dropped. So that means it has gained electrons. And gaining electrons means it's reduced. Over here is gone from a charge of 0 to positive 5, so that means it's lost electrons, and losing an electron means that it's oxidized. So from here we find out that the same species, AS, is getting reduced as well as oxidized. So what we do is we write down the oxidation and the reduction half reactions separately. In some other problems, you might have a different compound getting reduced and a different compound getting oxidized. So doesn't matter, we just have to write the oxidation half reaction separately and the reduction half reaction separately. So over here the reduction half reaction is AS goes to ASH3, which is right here, and oxidation half reaction, which is this one, is AS to H2ASO4. So step 1 is we find out the oxidation number. Step 2 is we write down the both the half reactions separately. And now step 3. We check in the 2 half reactions that we wrote separately. We find out whether the major atoms in each half reaction is balanced. So in this case, the major atom is AS. So we see that it is indeed balanced because there's 1 atom of AS here and there's 1 atom of AS here. And similarly in the reduction half reaction, they're again balanced. Major atom in both reactions is AS, and it is balanced. And step 4 is we start with balancing oxygen, and then if oxygen is not balanced, we introduce water and balance it that way. So we find in the oxidation half reaction that there's 4 oxygen on right hand side, but there is no oxygen on the left hand side, so we balance them by adding water. So 4 atoms of oxygen here, and we balance it by introducing 4 water. So 4 oxygen here, 4 oxygen here. And similarly in the reduction half reaction, there is no oxygen, so we don't worry about it because there is no oxygen here. Now you might wonder, okay, hydrogen, we introduced water here, but what about the hydrogen? That is step 5. We balance hydrogen by introducing H+. In the oxidation half reaction, there's 8 hydrogen on the left hand side and there's only 2 hydrogen on the right hand side. So there's an excess of 6 hydrogen on the left hand side. We balance that by introducing 6 hydrogen on the right hand side. So we can see the hydrogens are balanced. 6 hydrogen plus 2 hydrogen is 8, and 4 times 2 is 8. So hydrogen is balanced, and so is the oxygen. So 4 oxygen here, 4 oxygen here. Now in the reduction half reaction, we see that there is 3 hydrogen on the right hand side, but no hydrogen on the left hand side. So we balance that by introducing 3 hydrogen on the left hand side. So we can see that even in the reduction half reaction, there's 3 hydrogen on the left hand side, 3 hydrogen on the right hand side, and we don't have to worry about the oxygen here because there is none. And now step 6. Now that we balanced hydrogen and we balanced the oxygen and the major atom are also balanced, now we balance the charge. We see if the charge is balanced. Now we see here that there's 6 positive charges here, and this whole total ionic charge is -1. But there's 0 charges on the elemental form of AS, and there's 0 charge in water. So we see that 6 minus 1 is a total of 5 positive charges which are in excess on the right hand side. And how do we balance that? We balance that by introducing 5 electrons on the same side as the positive charge, because the electrons are negative. So we see that by introducing 5 electrons, there's 5 negative and then 5 positive. So the charges are balanced here. So similarly, in the reduction half reaction, we see that there's 3 positive charges on the left hand side, and there's 0 charge on the right hand side. So there is an excess of 3 positive charges on the left hand side. And how we can balance that is by introducing 3 electrons on the left hand side. So there's 3 negative, 3 positive, which is 0, which is the same as the 0 charge on the right hand side. Now that we introduced the electrons, now step 7 is we cancel out the electrons that we introduce by multiplying with an appropriate factor. And we see that in the oxidation half reaction, there were 5 electrons on the right hand side, and in the reduction half reaction, there were 3 electrons on the left hand side. But we have to cancel them out somehow, because we have to combine the reactions, adding them together later on, but we don't want any electrons in the final reaction. So the only way we can cancel them out is by multiplying by the common factor, which is 5 times 3 here gives us 15, and 3 times 5 gives us 15 here. So in that way we'll be able to cancel them, because there'll be 15 electrons on the right hand side and 15 electrons on the left hand side. So once we add them together, they will cancel out. And that's exactly what we'll be doing in step number 8, is we'll be adding the reactions. And step 7 was to multiply them. Step 8 is to add the 2 reactions together. Now once we multiply 3 throughout the entire reaction, gives us 12 water. 3 times 4 is 12, 3 times 1 is 3, 3 times 1 is 3, and 3 times 6 is 18 hydrogen, and 3 times 5 is 15 electrons. And same thing with the reduction half reaction. 5 times 3 is 15 electrons, 5 times 3 is 15 hydrogen, 5 times 1 is 5 AS, and 5 times 1 is 5 AS. And we add them together, 15 electrons on the left hand side, 15 electrons on the right hand side, they cancel out. So now we add them together, 12 water and 15 hydrogen, 3 plus 5 is 8, and then we write down 3 H2ASO4, and we write down 5 ASH3, and then the 18 hydrogen. Now there's 18 hydrogen on the right hand side and 15 hydrogen on the left hand side. So this goes into here, so this cancel out, and the remaining 3 hydrogens right here. So we rewrite the equation here. 12 H2O 8As gives 3H2AsO4 plus 5AsH3 plus 3 hydrogen. Now if the problem over here that was asked, if it had asked us to solve or to balance this redox reaction in an acid solution, this is where we would stop, and that would be our solution. But it asks us to solve it in a basic solution, so there's one more step involved, and which is step number 9. If the problem mentions basic, then we have to eliminate the hydrogen from the reaction. So, and the way we do that is by introducing water, but how we do that is, we have to cancel out this 3 hydrogens, so we make sure we write the self-ionization of water reaction in a way so that the hydrogens cancel out. So, for instance, if this was 6H plus, over here we would make sure we introduce 6 hydrogens on the left hand side to cancel them out, and that would mean that we would be introducing 6 H2O. But since this is 3, so we write down 3 hydrogen on the left hand side. We write down the reaction of self-ionization of water, and 3 H2O gives us 3 OH, 3 in the reverse. So 3H plus 3 OH gives 3 water. So these two cancel out. 12H2O minus 3H2O gives us 9H2O, and once we add these together, that would be our final solution with the 3OH, which makes it basic. So that's how we balance a redox reaction. Thank you very much.